Next, we'll consider a more rigorous description of the nonlinear polarizability at the molecular level based on time-dependent perturbation theory. This is more quantum mechanically founded, although the physical origins are still derived from this polarizability model, where we have electric fields that can slosh around inside a molecule that are enhanced close to electronic or vibrational resonance. So this allows us to address some of these limitations of the adiabatic polarizability. Specifically, it can't really be used to describe resonant interactions, either electronically or vibrationally, because it implicitly assumes that all excited state, all virtual states, are comprised of real states that are much higher in energy than the resonant interactions. So going on from there, I'm actually going to do things a little bit backward and tell you what the final result is first, and then back calculate and understand its origins. So the final outcome, and we're going to look at the two most common cases. One is second harmonic generation with electronic resonance at the doubled frequency, and that's indicated by the underscore. And the other is vibrational sum frequency generation, where the resonance is with an infrared photon, which is indicated by the underscore here as omega 2, but you can think of that as omega IR. So for the first case of second harmonic generation, the functional form for the molecular polarizability, it's a summation over many states. Each state has a resonant line shape function and two key terms in the numerator. And the first is the transition moment from state M to state 0, and the second one is the two-photon absorption matrix from state 0 to state M. So it's going from 0 to M and then M to 0. 2 photons up, 1 photon down. For the vibrational sum frequency generation, it looks quite similar in its functional form. Again, we have a line shape function, this time now with a resonance with omega 2, and in this case omega IR. And the two terms here, if we're starting right to left here, then it's going from the ground state to state N, where this is a vibrational excited state, and then a Raman transition from N back to ground state. So whereas electronic second harmonic generation looks as though it's 2 photon absorption followed by 1 photon back down to the ground state, vibrational SFG is the other way around. You have a 1 photon up to the excited state and then 2 photon Raman transition back down to the ground state. Okay, so that's what we're going to end up with. How do we get there? Before we go through nonlinear optics, let's start with linear optics. And the classic expression from time-dependent perturbation theory for the linear polarizability is given by this expression. It's a sum over states where you've got all these n excited states that are potentially contributing, and we're summing. If we can think about making this virtual state by taking a linear combination of real states. And it's not an eigenstate, that dashed line, it's not an eigenstate because it's not a time-independent state. It's a virtual state. So we can make that virtual state by, what's our basis set for describing that time-dependent virtual state? We're going to use a basis set built up of stationary states, and those are the real excited states. And so that's where this summation operator comes from. It's basically describing that virtual state by the linear combination. The contribution from each of those excited states to the linear polarizability has to do with the magnitude of the transition to that state and the transition back down, and the energy gap between the virtual state and the real state. And so this, for example, if we're considering just this red state, then it'll be the transition moment here and here that will describe it. I'll get to the second term over here in a minute. If I'm moving on to the next state, then there'll be another transition moment term and another frequency term, and eventually we're going to get further and further away in frequency, and so by scaling for this energy difference, it's going to matter less and less. And so it's really those low-lying excited states are going to contribute most of the polarizability of these virtual states, especially if we're close to resonance as depicted in this energy level diagram. Okay, so that describes this first term, where the energy difference is what's giving rise to this resonance enhancement. What about the second term? And that arises because quantum mechanics doesn't know or care. You haven't told it that you're starting out in the ground state. The same equations are very general. They apply no matter what your starting state is. And if we look at this in terms of energies, bearing in mind that h bar omega is actually an energy, if we're starting out at the ground state, if we have a transition that is below, not the ground state, our initial state is state 0, whether it be that ground state or an electronic excited state, if in this case it actually is an excited state that we're starting out in as our initial zero state, and we have a real state that is below that state in energy, this would be, for example, approaching a stimulated emission transition from a population initially in the excited state, then the resonance enhancement is going to come from the fact that this h bar omega 0, this term here, can be a negative energy relative to your initial state. And if this is negative, then now you can have a resonance enhancement of this term on the right. So both of these contributions are formally present in the linear polarizability, although, as you can imagine, if we're starting out in the ground state, this first term is really going to be the driving interaction 9 times out of 10. Okay. So that gives us our linear polarizability, and it's a good starting point for trying to figure out what's going on with the nonlinear polarizabilities describing both second harmonic generation and some frequency generation. You've seen the end results. We know what's in the numerator and the denominator. These are the form of the line-shaped functions, and they look very similar to the line-shaped functions right here. So this is the form of the line-shaped functions. They look similar to those that we saw in the linear polarizability, except the resonance enhancements are slightly different. Okay, so how do we get these expressions, these two expressions, from time-dependent perturbation theory? Well, for a 2-photon interaction for the linear polarizability, we only had 2 possible orderings, the one on the left in red and the one on the right in blue. Those are the only 2 ways to arrange the light-matter interactions to get from the ground state back to the ground state with those 2 arrows. In nonlinear polarizability, we have 3 photons that we're considering, or 3 waves, actually 3 wave interactions that we're considering, and that gives us 3 factorial instead of 2 factorial, which was 2. We now have 6 different combinations, and they're depicted down here in terms of the different orderings of omega 1, omega 2, and omega sum that get you from your initial state back to your initial state. That's indicated by the I. And so this is just quantum mechanics telling you these are the ways that you can arrange these different light-matter interactions. The next question is, how does that relate back to these 2 expressions up here on the right? Let's do the first one first, the second one first, for vibrational sum frequency generation. So for vibrational SFG, we know we have a real state that has to be resonant with omega 2, with the transition from the ground state to omega 2. So that would correspond to a real state right here, which, if we go through all of these 6 and ask which ones yield a resonance enhancement with a real state at that energy, omega 2, it's just these 2 terms, the ones in B and D. Those are the only 2 contributions that are resonantly enhanced by a real state present at the energy corresponding to h bar omega 2. So we can group, we can pull out. So these are the 2 resonant terms that I've sort of lumped out here. This red one corresponds to that one, the blue one corresponds to that one. We can pull out this constant factor of the resonance enhancements. This term right here and this term right here we can pull out. And the other thing that also we can pull out is this term right there, the transition moment from 0 to P. So if we pull that out, then what we're left with inside the brackets here is actually, if we pull in one of these factors of h bar, it's actually the definition that we just saw previously for the linear polarizability, except modified slightly in the sense that we're starting from state P and ending up back at state I. So that would be, let me just highlight that a little bit better. That'll be this interaction. The photon there and or the field there and the field there that takes you from state P back down to your initial excited state, which actually corresponds to a Raman transition. Those 2 terms. Let's see. These 2 terms. And these are just the 2 different time orderings of those same interactions that will give rise to the linear polarizability describing the Raman transition from state P to state I, which is the anti-Stokes Raman transition. So just by definition substitution for the anti-Stokes Raman transition, then you can rewrite this as in this contracted form, where we lump all the rest of these interactions that we don't consider from this resonance enhanced term into a non-resonant term, which also technically still has a tensor form. So the resonant sum frequency generation can be written as this line shape function, complex line shape function term, and what's in the numerator, which is the transition moment from ground state to vibrational excited state, and then followed by the anti-Stokes-Raman from that vibrational excited state back down to the ground state. And that describes the polarization dependence as well. So the advantage of these contracted sum over states is that you actually don't have to go through the time-dependent perturbation theory to figure out what they should be. All you really need to know is that you've got a real state right there, and then from the presence of that state, that you can look at the energy level diagram and know what the correct answer is going to be. So the general strategy is find the resonant interaction, group everything else into the non-resonant terms or pathways that connect back to the ground state, and then contract things down from there. Okay, so we can move on. Just another example. The same general formula can be used to describe four-wave mixing. It starts out being headache, right? Because you've got now 4 factorial, which is, let's see, 6 times 4, 24 different pathways to consider. In the most general case, that's 24 quadruple products of transition moments for bookkeeping to describe the sum over states expression for four-wave mixing in the most general case, which is a pain. But if you use these contracted sum over states expressions, just grouping terms together, you can see that if there's a real state, we can group them up into 2 different classes of resonant kinds of interactions. If there's a real state here at the sum of omega 1 and omega 2, then you have something that looks like a 2-photon transition up and a 2-photon transition down, and that gives you this expression, this term right here in the sum over states, if Q is electronically resonant. If Q is vibrationally resonant, then where you've got a Raman transition from 0 back to Q, and then Q back to 0 again, that looks like this term right here, where you have a resonance enhancement at the difference frequency, if we put a minus sign in there, between omega 1 and omega 3, and the real transition between between the ground state, your initial state, and Q, the excited vibrational state in this case. So just by looking at these energy level diagrams, it's pretty easy to write down what each of these terms necessarily has to be in terms of what's in the numerator and what's in the denominator. If there's degeneracy in cars, then omega 1 and omega 2 become equal and therefore interchangeable. And so you have this factor of 1 over 2 factorial that shows up in the description of the vibrational term, but otherwise it looks remarkably unchanged. In the case of the electronic resonance, you technically actually don't have to include that factor of 2 in here, because that factor of 2 factorial is already inherently folded into the definition of the 2-photon absorption, because that's where that degeneracy actually manifests in this term. All right, but at any rate, just a little bookkeeping thing about factors of 2. The most important aspects of it with respect to polarization dependence is the functional form of the numerator in each of these 2 resonance enhanced cases. The denominator matters in terms of interpreting the spectroscopy and where the resonance is and how the complex line shape function plays out when you're detecting the intensity. So to summarize briefly, if you can convince yourself that the sum over states expressions really are quite reliable for describing nonlinear polarizabilities through this contraction approach. So what it allows you to do is just look at an energy level diagram, group terms, and write what the resonant part of the nonlinear polarizability should be, and everything that doesn't contribute to that resonant interaction is lumped together into the non-resonant term. So it's a very actually simple and intuitive way for simplifying the molecular interpretation of nonlinear polarizability without the need for any additional assumptions or approximations beyond the validity of time-dependent perturbation theory itself.